Hello and welcome. Excuse me. Hello and welcome to Office Hours round 3. Today is going to we're going to start with the. Sorry, I just realized that I spelled hello with a W, and I have no idea why. Today's going to be the conclusion of our two-part review. Last week was last Wednesday was sig figs. We're gonna kick things off with a mini lecture on unit conversions, and then it'll be open office hours, and we can talk about anything you want to. Like, for example, the boss level problem we wrote in lecture this afternoon. So I'm going to go ahead and get to it. I believe that the unit conversion lecture will take less time than the sig figs lecture. So we'll get through that, and then we'll talk about anything you guys want to hear, and any questions that have been submitted through email. All right, so let's go ahead and dive in. Hang on, there we go. Okay. So we are going to talk about unit conversions. All right, all unit conversions require a ratio. I guess if we want to go even more kind of primordial, a unit is just a defined measure of some physical quantity. It could be length, area, volume, mass, you name it. If it is a physical quantity that can be measured, we have, as a human species, developed units to quantify those measurements. Now, a unit conversion is just a simple ratio. So, for example, we're going to be doing a lot of examples today. If I asked you how many inches are in 3.94 feet? Well, to do this, to determine it, sorry, I just realized I use in for inches, and then I use the word in the sentence. It's a little confusing. I'm gonna actually spell the unit out. There we go. How many inches are in 3.94 feet? To solve this problem, we need to know the relationship, the ratio between inches and feet, right? And the ratio is there are 12 inches in 1 foot, all right? And with that equivalence, with that ratio, or that equivalence can allow us to write two ratios. We can write this as 12 inches per 1 foot, or we can write it as 1 foot per 12 inches, and both of these are equally true, right? Either we can use either when we're solving problems. So to convert 3.94 feet to inches, we need to set up a ratio. Now, like I said in class, look at what unit you want to cancel and what unit you want to be left with when deciding how to arrange your ratio. We want feet to cancel here, so I'll put it in the denominator. We want to find inches, so those go in the numerator. And then once you have your unit set up to cancel properly, add the numbers, right? 1 foot is 12 inches, and now we're good to go. Feet cancel feet. and we're ready to crunch some numbers. Now, excuse me, opening up the calculator, 3.94 times 12 divided by 1. Now, the value my calculator is giving me is 47.28, all right? That is the correct value. The correct units are inches, but we need to ask ourselves, how many sig figs can we keep? And the answer is, we have our original measurement, which is 3.94. It has 3 significant figures, so we can only keep 3. 8 is going to round up. So our correct answer with the correct units and the correct sig figs is 47.3 inches. All right. Now you may be asking, wait a minute, Josh. 3.94 has 3 sig figs, but 12 looks like it has 2, and 1 foot looks like it has 1. So why didn't we round our answer to 12 or 1? And the answer is that this ratio, right? The ratio 12 inches in 1 foot, this ratio is not measured. It was not measured. It is a definition. All right? It's not measured, it's a definition. That means that there's exactly 1 foot in 12 inches. There's exactly 12 inches in a foot. So because this ratio wasn't measured, because it's based on a definition, it will never limit your sig figs, all right? And this is a huge take home. So whenever you perform a conversion within a unit system, or I should say a measurement system, and by measurement system, I mean English, like within the English system, or, for example, within the metric system, as long as the units are all within the same system. The unit conversion will never limit your sig figs. All right, whenever you perform a conversion within the same system, metric unit to metric unit or English unit to English unit, your unit conversion will never limit your sig figs. When you convert between systems, it can. And the reason why is when you're going English to metric, that's not based on a definition. That's based off of a measurement. You have to measure that quantity. Here, hang on 1 second. Sorry, I just got a phone call from my wife who's in this house, but then when I picked it up, it was there was nothing, which makes me think that my 2-year-old stole her phone. And anyways, I apologize for that strange interlude. All right, so let's get back. So we have, so within the same system, no sig fig limit. From in between systems, they can. All right, and here's what I mean by can. Let's look at a couple more examples. All right, let's convert 14.06 centimeters to inches. All right, now again, we need the unit conversion, and the unit conversion is 2.54 centimeters or in 1 inch. All right, this is measured, so this unit conversion has 3 sig figs. All right, let's use it to convert 14.06 centimeters to inches. We put centimeters in the denominator, inches in the numerator, and 1 inch is 2.54 centimeters. Now we crunch our numbers. We have 14.06 divided by 2.54. This comes out to be 5.5354, 3307 inches, right? Because centimeters cancel. Now we have to look at our sig figs. 14.06 has 4, 2.54 has 3. So since 3 is less, right, we're doing division, we're limited to 3 sig figs. This 5 will round up. So our final answer will be 5.54 inches. So the correct value with the correct units and the correct sig fig. So in this unit conversion, in this unit conversion, our conversion actually limited our sig figs because it only has 3. Let's do a second example. All right, with where we want to convert 2.2 inches to centimeters. All right, so we have 2.2 inches. We want inches to cancel, so that goes in the denominator. We want to be left with centimeters, so that goes in the numerator. And now we know that 1 inch is 2.54 centimeters. Inches cancel inches, and we're ready to crunch our numbers. 2.2 times 2.54 is 5.588 centimeters. Now you'll notice our unit conversion has 3 sig figs, but our initial length only has 2, so we're going to have to round to 2. In this case, our unit conversion does not limit our sig figs. 8 rounds up, giving us a final answer of 5.6 centimeters. All right, so when you are converting from one system of measurement to another, watch out for sig figs. When you are converting within a system, you do not need to worry about it, right? Now, a couple things. We're actually not quite done with unit conversions. The primary system of measure we will be using this semester is the metric system. And the reason for this is the metric system has a base unit for, well, here, let's talk about the metric for a minute. The metric system. The metric system has a standard unit for mass, which is called the gram. abbreviated with a lowercase g. It has a base unit of length, called the meter, abbreviated with a lowercase m. It has a base unit of volume, called the liter, and this is abbreviated with a capital L. Now, the reason why the metric system is the preferred system of science users all over is because it's very, very versatile. It's very flexible. There are these base units of measure that can be modified to fit your needs depending upon whether you need very large numbers or very small numbers, all right? And they do this by using a system of prefixes. All right, there is a prefix system that is employed that allow us to modify the metric units, all right? So so you have, for example, the prefix kilo, which is abbreviated with a lowercase k, and when you attach this to any unit of measure, kilogram, kilometer, kiloliter, it means it is 10 to the third times a gram. So there's 10 to the third grams in 1 kilogram. And there's tons of these. If you crack open the first page of your textbook, you're going to see a giant table of all of these. We don't need all of them, but I'm going to zero in on the important ones, the ones that I would recommend that you learn, become familiar with, or at least commit to memory. All right, so there's kilo, centi is another one. The prefix is a lowercase c, and this is 10 to the negative second. Milli has a prefix of m. It's 10 to the negative third. Micro sorry, I'm just cleaning up my milli. Micro has a prefix that is the Greek letter mu. That's the Greek letter for m because m was already taken for milli. And that is 10 to the negative 6. Nano, which is a lowercase n, is 10 to the negative 9. And pico, which is a p, is 10 to the negative 12th. All right. Now, these right here, when I teach this class in a actual physical classroom, I tell my students that they have to memorize these, that I don't provide them on exams. Now, as you know, your exams are open book, open internet, open anything. So technically, you don't need to memorize anything for this class. However, I would recommend committing these to memory because in a testing situation, if you are having to stop and look up what these are, if you don't just know them off the top of your head, you're going to lose valuable time. And we use these 6 so frequently that that they're really worth your time to just know. So I would commit these 6 to memory. Again, there's like 14 plus in your textbook. We don't need all of them, but we do need all the small ones because this is chemistry. We're dealing with atoms, we're dealing with molecules, we're dealing with things that are very, very, very small. Sorry, Ludwig, I'm just now seeing your comment in the chats. All right. Now, let's go ahead, now that we kind of have seen, okay, this is how the metric system works. Let's put this into practice and get some reps converting between metric units. All right. So, let's convert I don't know, let's do 15.6 centimeters to meters. All right. Now, here's how you use that prefix table that we're let me try to re-English that. Here's how you use that prefix table that we were looking at on our the slide that came right before this one. All right. So we've got 15.6 centimeters. We want to convert to meters. All right. First, we do the setup. Centimeters goes in the denominator. Meters go in the numerator. Now, what those prefixes, you'll remember that centi, the prefix meant 10 to the negative second. That tells you that 1 centimeter is 10 to the negative second meters. Centimeters cancel. And now we multiply on through. My calculator is telling me that the answer is 0.156. We know our units are meters. And we know as far as sig figs go, we're starting with 3, so we have to end with 3 because, again, we're moving from metric unit to metric unit. So our unit conversions will never limit our significant figures. All right, let's do another example. Let's convert 87.0 liters to milliliters. All right, so we're going to take 87.0 liters, and we're going to put liters in the denominator, milliliters in the numerator, right? Because we want liters to cancel. And milli is 10 to the negative third. That tells you that 1 milliliter is 10 to the negative third liters. All right? Liters here cancel. And when I multiply this through, when I punch it into my calculator is telling me my answer is 87,000 milliliters. All right, now we have to ask ourselves, how many sig figs should we have? And 87.0 has 3 significant figures, whereas our answer only has 2. And you'll notice that if you add a decimal place, you've gone from 2 sig figs to 6. So that's not correct. But 2 sig figs is equally incorrect. Now, how do you write 87,000 with 3 sig figs? The answer is scientific notation. We're going to take our decimal and roll it over 1, 2, 3, 4 spots. So we can write 87,000 with 3 sig figs as 8.70 times 10 to the 4th milliliters. All right, and that is our correct answer. Correct value, correct units, correct sig figs. All right, those are some metric unit conversions. Now you'll notice, actually, before I zero this out, that we have in both of these problems started with a modified unit and moved to a base unit, or in the second one, we started with a base unit and moved to a modified unit. What happens when we're given a problem like the following? Where we have to convert um 1.0126 milligrams to nanograms. All right, you'll notice that here we start with a modified unit and we end with a modified unit. Now here's the problem. All of our prefixes in that table only give us the unit conversions from going to and from a base unit, right? We could go from milligrams to grams, but we can't go from milligrams directly to nanograms, all right? Those prefixes allow you to jump back and forth from base to modified or from modified to base. In a problem where you're going from one modified unit to another, you're going to have to do this in two chunks. We are going to have to take our milligrams, convert it to grams, and then, once we're in grams, take our grams and convert to nanograms, all right? So this is going to be a two-step unit conversion. First, we're going to take our milligrams, 0.0126 milligrams, and we are going to throw in a unit conversion to convert from milligrams to grams. Now, 1 milligram is 10 to the negative third grams, all right? And you'll notice we got milligrams canceling milligrams, but we're not done with our unit conversion because we want to convert from grams to nanograms. All right? And 1 nanogram is 10 to the negative ninth grams. So here, our base unit cancels, grams cancel grams, and now we're ready to crunch our numbers. All right? You punch this into your calculator, and your calculator will give you 12,600 nanograms as your answer. You'll notice you start with 3 sig figs, so you got to end with 3 sig figs because we're within the same measuring system. We're going metric to metric. All right. So those are unit conversions in a nutshell. We will be doing them over and over and over this semester. And again, if I could jump back to this, I can't emphasize enough how important getting all these guys down. All right. Because it involves conversions of volume, of mass, of length, even things we haven't talked about yet, pressure, etc. You'll be using these prefixes over and over. So I heartily recommend getting a lot of repetition in and becoming very comfortable with these unit conversions. All right. So let's see, where are we at? All right. I said that the unit conversion lecture would be a lot shorter than the sig fig lecture, and it looks like we're clocking in at about halftime. So, as of right now, we are in open office hours, and we've already had our first request to get some reps in with that boss level problem. Give me a second, I'm pulling it up from my lecture notes. Ooh, think it was here. All right, yeah, so, okay, here we go. Let's take a look. So I'm just going to rewrite it for those of you who may not have it at the ready, so the video will have a self-consistent context. But here's the question. How many molecules of water are in 1.00 mils? And we are given the density of water is equal to 1.008 grams per milliliter. All right. Now, this question is an excellent simulation for a testing scenario. All right. It's a great way to prepare for the exam, and here's why. You've never done a problem like this before, and I guarantee you'll feel this feeling on the exam or the exams. The prereq exam, maybe not. Depends upon how sharp you are in your prereqs. But starting with exam 1, you will definitely be faced with a problem that you've never done before and that I've never done for you. And the reason why that is because in a testing context, I want to know, do you understand? Can you problem solve? Can you think? You may not have done this exact problem, but there's enough information in the problem for you to solve it. So let's talk about how you take a problem that you've never done before and get to the answer. All right, so let's break things down. The first thing you want to do is identify, what are you trying to find? All right, what are you trying to find in this problem? And the answer that we're looking for is we're looking for the molecules of water, the number of water molecules. Right, that's what we're trying to find. Once you know what you're trying to find, that sets you up for your goal. All right, our goal is waters of molecules of water. Now let's look at what we're given. All right, this is the data. This is the stuff that we've got to use to solve that. All right, the first thing that I notice is that we're given a volume of water. We're told that we have a volume of 1.00 milliliters right here, right? Volume. We're given a volume of water. Second thing that we're given is we're given the density of water. All right, the density of water is right here. Now, this one is important. They're both important, but this one particularly so. There's another piece of information here, and that is density. There's an equation for calculating density, all right? Density has an equation, and anytime you're given a quantity that corresponds to a mathematical equation, you need to write that equation down under your given information, because that equation will be critical to solving the problem. The equation for density is this. Density is equal to mass over volume. All right? Now, let's look at this equation. In this equation, we've been given density. We've been given volume. So this equation allows us to solve for mass. Right? Mass. Is mass what we're looking for? The answer is Not exactly. We're looking for molecules of water. But does mass relate to molecules? And the answer is absolutely. Because you can convert grams to moles, right? And we got plenty of reps today converting moles to molecules or atoms, right? So we know how to take a mass, convert it to moles. We can take moles, convert it to particles. So we need to use the equation for density to find our mass of water and then perform our unit conversions to go from mass to molecules, all right? So even though we didn't know how to do this problem, we never worked this problem before, we have the ability to solve it, right? We have all the tools. We just had to figure out how to put the puzzle pieces together. And more often than not, let me just emphasize this, the key to putting all those pieces together will come from the mathematical equations that correspond to the information given in the problem. All right, now that we've conceptually set up how we're going to attack this thing, let's start breaking it down one step at a time. Step number one, we need to take our equation for density and isolate mass on one side of the equation. All right, so we're going to do that by multiplying both sides by our volume. So volume will cancel on this side, and our equation rearranges so we get mass is equal to, or actually, I'll write this up here. Mass is equal to volume times density. We plug in our value for volume, 1.00 milliliters, times our density, 1.008 grams per milliliter. Now, milliliters are going to cancel because this one is in the numerator and this one is in the denominator. All right, so our mass turns out to be 1.008 grams of water. All right. Now, when we look at our sig figs, our volume has 3 sig figs. Our density has 4. So our answer, the product of these two quantities, can only have 3 sig figs. I'm going to wait to round to the end of this problem, but I'm putting these lines to remind myself that this number only has 3 sig figs. All right. Now that we know our mass, remember our game plan. We've found our mass, and now it's time to do our 2-step conversion to get from mass to moles and then from moles to molecules, all right? So we have 1.008 grams of water. All right, but remember, only 3 sig figs. Times, we need a unit conversion that'll go from grams of water to moles of water. And then we need a unit conversion that'll take us from moles of water to molecules. All right, now we know the second one, right? 1 mole of water has 6.022 times 10 to the 23rd, right, molecules of water in it. But what about this guy here? What about moles of water to grams of water? Now, when we were doing earlier today in lecture, we did atoms, right? We had like, oh, you got 5 grams of copper. We could use the atomic mass to convert from grams of copper to moles of copper. But you will not find H2O on the periodic table because the periodic table only has elements. It doesn't have molecules, all right? So to find the unit conversion, to go from grams of a molecule to moles of a molecule, you have to calculate what is called the molecular mass. All right? The molecular mass is the sum of the atomic masses in a molecule. All right, we need to calculate the molecular mass for water. All right, oxygen, if you look it up, has an atomic mass of 16.00. Hydrogen has an atomic mass of 1.01. All right, but we have 2 hydrogen atoms in this molecule. So we have to add the mass of 2 hydrogen atoms. When you do, the molecular mass of water comes out to be 18.02. You'll notice that all 3 of the numbers we added together have their last significant digit in the second decimal place. So does our answer. So we do not need to round. So 18.02 grams per mole. This is the molecular mass of water, and that is what we plug in right here. 1 mole of water has a mass of 18.02 grams. And now, with that unit conversion, grams of water cancel, moles of water cancel. We are ready to crunch our numbers and calculate our number of molecules. So we have 1.008 divided by 18.02 times 6.022 times 10 to the 23rd. All right, so the value that I'm getting here is 0.33. Oh wait, hang on. The value I'm getting is 3.3685771 times 10 to the 22nd. Let's look at our sig fig situation. Our mass, as we've already stated, has 3 sig figs. Our molecular mass here has 4, and Avogadro's number has 4. So we have to roll with the fewest, right? We round to 3 sig figs. 1, 2, 3. And so our correct value with the correct number of sig figs and the correct units is 3.37, because again, 8 rounds up, times 10 to the 22nd molecules of water. All right. And so, Ludwig, it looks like you were 100% correct. You got this spot on. That is the number of water molecules inside 1.00 milliliters of water. All right. And so that is the boss level problem that I left you with in lecture. I hope you had as much fun as I did doing it just now. And yeah, so I am at this point. I'm going to check my email to see if we have any email submissions for questions, and of course, if you have any questions, any of you who are watching with me live, I will totally answer yours first. But in the absence of any live questions, I will I'll start getting to some email ones if there are any. Let's see. Last week's Sig Fig lecture. Yeah, totally, Anthony. We could totally hit up that business. Let's see. I was curious about how you would get the uncertainty. Oh, okay, yes, yeah, totally, Anthony. Great question. Excellent question. So, so the number that I gave was so for a measurement. For the measurement of a number like the one that I used in lecture last week, that was I believe it was 510,000. I don't remember the unit, so I'm just going to throw grams on there. Anytime you look at a measured number, the last digit is the uncertain digit. That is the uncertain digit, which means what it means to be the uncertain digit is that the true value of the mass rounds to this place value. Whatever object was measured that has a mass of 510,000 grams was measured on a device that could only read to the 10,000s. All right, that means it's not that there are absolutely 4 zeros following that one, but what it does mean is the device wasn't precise enough to be able to tell any variation after that place value, and so the true value of that mass is any number that rounds to 510,000. All right, and that range, the largest number, the largest possible number that rounds to that place would actually be 514,999. Still rounds, right? Because 4 rounds down. So this still rounds to 510,000. And the smallest possible value that the true value could have would be 505,000, because that 5 rounds up to, that 5 rounds up to 510,000. So that's how I got the uncertainty range. Is you take whatever your measured value is, find the uncertain digit, and your range is going to span from the largest number that would round to that value and the smallest number that would round to that value. Does that make sense? let me know. Let's see, Eric. I'm not sure if I already covered this, but how do you do the atomic nuclei in the homework number 33? Okay, Anthony, you're welcome. Okay, Eric, let me see. All right, Leanna, let's see. I got the same answers, Ludwig, when doing the challenge problem. It made me wonder, will we be required to use... Leanna, great question. That is an excellent question. So, Leanna, you will not be required to use a specific periodic table. Any periodic table will work just fine. And I account for this either by, because there's a range of values that are floating out there. Either I take that into account, so I engineer the problems to make sure that if it's a numerical entry, that no matter what periodic table you're using, it comes out the same. Or if there's too much variation, depending upon the specific problem, then I just make it multiple choice, so you just pick one that's correct. Okay, Jason, this is worth addressing for sure. That value for hydrogen is wrong. That value for hydrogen is straight up wrong. If you use that value for oxygen, you're going to be fine. But hydrogen... When you're talking about hydrogen, if you look up any periodic table, hydrogen will have an atomic mass ranging from, on the simpler side, 1.01 AMU, all the way out to 1.0079 AMU. But if you have a value for hydrogen that's 0.0899, either you wrote it down wrong, or the periodic table you have is fatally flawed. And if you're ever wondering, okay, yeah, there we go. Jason, if you if you repeat the calculation using 1.00794, you will totally get the right answer. Because your hydrogen mass, your water mass for water will be 18.7 something. It'll be a lot closer. Okay, Eric. Okay, sorry. You said exercise 1. Here, let me pull it up real quick. All right, let's see. Let's go to, okay, here's our lab. Let's go to assignments. And check out exercise 1. You said number 30 something. Oh, right. Okay, Eric. I've not already gone over this. Let's see. Wait, hang on. Okay. Okay, I think... Whoops. Goodness gracious. Okay. So there's an exercise 1. This is the one where they ask. Well, I was about to say I ask, but I didn't write this problem. Well, this part was my bad. It says the atomic nuclei atomic nucleus has a diameter of, it just is 1 times 10 to the negative 13th, but doesn't give you any units. So it's 1 times 10 to the negative 13th centimeters. Now that you have a length unit, this is just one long unit conversion problem, because this problem gives you the ratio that there are 1 times 10 to the negative 13th centimeters in 1 nuclei. Or in 1 nuclei, there is 1 times 10 to the negative 13th centimeters. So now that this has units and you have 2 unit conversions, you can use one of these to yes, okay, and Eric, it totally wasn't your bad. There's a typo where the unit was left out. So that was not your bad at all. Alrighty, so I'm still working on making it through my emails, but of course, as I do that, I'm down to answer any and all questions. Oh, let's see. Then I totally can. I just need a little more information. Oops, not there. Let me know if that's the question that you were needing a jump start on. Okay, sweet. Okay, so here's the thing. So we are, we're given in this problem, we're given that we have a price of gas that is $1.33 per gallon. Holy moly. That is something, yeah, that's just unreal. And we're asked, what would the cost be in, we want to know how many cents per liter. All right. So we have to do 2 unit conversions here. The first is we need to convert from dollars to cents. Dollars to cents. And there is for every $1, there's 100 cents. And this is exact, right? It's not like we went out in nature and measured, in nature, there's 100 cents in a dollar. This is a definition. So that will not limit our sig figs, right? Dollars will cancel dollars just fine. Sig figs aren't affected. Now, to convert from gallons to liters, takes us from one system to another, right? The unit conversion is one, because gallon is an English unit, liters is a metric unit. 1 gallon is 3 0.785 liters. All right. And this right here is measured. It's measured. So our sig figs matter. All right. So you crunch your numbers, but when you look at it, whatever our answer is, when you look at your conversion from gallons to liters, there's 4 sig figs. And then when you look at your initial quantity, you had $1.33 per gallon. That has 3 sig figs. So whatever your answer comes out to be, it should only have 3 sig figs. All right, because our starting value has 3. Our unit conversion from dollars to cents won't limit us, but our unit conversion from gallons to liters has the potential to. It just has 4 sig figs. So we're going to be limited to 3 significant figures. So that is how you handle that problem. All right, and again, I am 100% interruptible, but until I get hit with the next question, I'm going to go and keep working on our first what's that thing called? Lab experiment. Almost ready to launch. Anytime. Let's see. Um, Leanna, great question. So, on the exam, I would say little to nothing is provided, because um, little to nothing is provided because the exam is open book, open notes, open lecture, open internet. It's open everything. Um, so there is no specific formula sheet that's provided for the exam. That being said, I totally encourage everyone to make their own personal formula sheet. Like, make a thing with all the information that you think you could possibly need as a quick reference, that you don't have memorized, that you don't know off the top of your head to look at and reference when you're taking the exam. So no unit conversions are provided, no equations are provided, because it's open everything. So that's kind of what I encourage everyone to do, and the process, the act of making that reference sheet is a good way to study for the exam as well. So there's a verbal answer to your typed question. Hey, Leanna. Good to see you. Here, let me get you on the right track. With that problem, again, I can't spill specific answers because the assignment is still live. But I can get you on the right track there. So Angstoms which bear the abbreviation. It's the capital A with a little weird circle up top, like a little halo. Here is it. It's a length unit that is very, very close to nanometers, actually. One angstrom is 10 to the negative 10 meters. All right? And so when you need to convert from miles to angstroms, it's basically a unit conversion where you have 1.0 miles, and you gotta have, and this is going to be a multiple step unit conversion, but you gotta find a way to convert your length in miles to meters, and then once you're in meters, you can use the nifty unit conversion. 1 angstrom is 10 to the negative 10th meters. So hopefully that's enough to at least get you going, get you started on this unit conversion problem. Again, I can't give a specific answer because the assignment is still live. But good to see you, to see somebody towards the end of office hours. I'm there's always that lingering question in my mind where it's like, is it even worth hanging out? Is nobody gonna come ask any questions? Am I just, well, I'm not twiddling my thumbs. I'm doing class stuff, so I'm getting work done. It's productive time, but I always like when I can be helpful to students during office hours, because that is why I hold them. So thanks for the ninth inning question here. Dude. Oops. There we go. Dude, well done. I mean, here's the beauty of this like long chunk of office hours that we have is you can use the time exactly as you have been by working on an assignment. And yeah, like exercise 1 is stinking long. But if you're doing it while I'm here live streaming, even if I'm not actively answering questions, whenever you hit a snag or a problem where that's like, how do I handle that? That I'm not exactly sure how to go forward. You can actually get a live response as opposed to like sending an email, waiting for a response, all that stuff. I think it's an excellent way to use these nice big 3-hour swaths of time that we have here twice a week.